Today we're tackling time series analysis, specifically the theory behind it all, how we decompose, how we clean up, and model these signals that change over time.
That's the plan.
Our mission here isn't really to get lost in the weeds of computation, but more to give you a solid conceptual map. We want to focus on the why and the how behind smoothing, detrending, deseasonalizing. Think of it as a way to grasp why these tools are used and, well, how they fundamentally shape analysis.
Exactly. Fundamentally, the objective, if you boil it right down, is taking that raw, often messy, time series data and stripping away everything that isn't stable, isn't stationary.
Oh, okay.
We're trying to precisely estimate and then pull out the long-term trend and those repeating seasonal patterns.
Yeah.
What should be left? Ideally, just pure, stationary, random noise. If we get to that point, we've basically succeeded.
Let's unpack that. The usual starting point is classical decomposition, right? We often begin by assuming the simplest case.
Yeah.
The series is just the sum of its parts.
Right. Trend plus seasonality plus noise. That's the additive model.
But as you mentioned, reality is often messier. That simple additive idea hits roadblocks pretty fast.
It really does, because
Right.
often the size of those seasonal swings isn't constant. It actually grows or shrinks as the overall level or trend changes.
Right.
That's multiplicative seasonality, where the components interact, they multiply. And trying to estimate components that are multiplying together like that, mathematically, it's much, much harder.
So how do analysts deal with that? Is there a way to handle that multiplicative interaction without making the math intractable?
There is. We use a really important technique, a conceptual tool called the variance stabilizing transformation.
Okay.
And almost always, in practice, this means taking the logarithm of the time series data.
The log transform.
Exactly. The insight here is that the log transform converts that tricky multiplicative relationship into a much simpler additive one.
Ah, I see. So taking the log turns multiplication into addition.
Precisely. It turns a complex interaction problem into a straightforward addition problem. This lets us use the standard, much easier additive estimation methods. It's really the key trick that makes a lot of real-world seasonal data manageable.
That's a critical point right off the bat. Okay, so with that transformation in our back pocket, let's shift to the actual methods people use, starting with techniques maybe more geared towards visualization or getting a first look.
Yeah, let's start with finite moving average smoothing. It's probably the most intuitive non-parametric approach.
Non-parametric meaning we don't assume a specific mathematical form for the trend.
Correct. The core idea is simple. If the noise component is truly random, stationary noise, then its average value over some window of time should be roughly 0, right?
Okay.
So by averaging the series over a defined window, say 5 points, the positive and negative spikes in the noise tend to cancel each other out. They get dampened. What's left is hopefully a smoother estimate of the underlying trend.
So the smoothing really hinges on that noise averaging out to 0. But what happens when you've got seasonality in the mix? The window choice becomes much more critical then, doesn't it?
Absolutely critical. If you want to smooth out seasonality, you need to pick a window size that exactly matches the seasonal period. So if you have monthly data with an annual pattern, you'd use a window of size 12.
To capture one full cycle in each average.
Exactly. That way, the seasonal highs and lows within that window average out, effectively removing the seasonal component. But there's a catch if the period is an even number, like 12.
Right. You can't center an average of 12 points perfectly on a single time point.
You can't. If you just average 12 points, the result falls between 2 time points. To get a trend estimate that aligns perfectly with the original time points, you need a slightly more complex centered moving average.
How does that work?
It involves giving half the weight to the first and last points in that window. It's a bit of a mathematical adjustment, but it ensures the smooth value is properly centered, lining up with the actual observation times. This allows us to knock out seasonality while keeping the trend estimate correctly aligned in time.
Okay, that makes sense. And once you have that initial trend estimate using the right moving average, then you get into that iterative decomposition process.
Yes, the typical 4-step approach for season decomposition, it's all about refinement.
Walk us through it quickly.
Okay, step 1. Get that initial trend estimate, often using that centered seasonal moving average we just discussed. Step 2. Estimate the raw seasonal component, usually by detrending the original series, subtracting the additive case.
Right.
Step 3 is crucial. Correct those raw seasonal estimates. For an additive model, the seasonal factors across one full cycle must sum perfectly to 0. For multiplicative, their product must be 1. You adjust them to meet this constraint.
So you enforce the definition of seasonality.
Exactly. Step 4. You now have a better estimate of the seasonal component. You can deseasonalize the original data. Then you apply a simpler smoother, like a short moving average, to this deseasonalized series to get a refined trend estimate. And finally, step 5, the residual noise. The original data minus your final trend estimate, your final seasonal estimate. It's a structured way to isolate each piece iteratively.
That seems logical for handling basic trends and seasonality, but here's where I think it gets really interesting. What if the trend isn't just a smooth line? What if it bends and curves quite a bit? Simple moving averages seem a bit rigid for that.
That is definitely a limitation. And that's precisely where lowest smoothing, or locally weighted regression, comes in. It's also non-parametric, so no assumed shape.
Okay, how is it different from a moving average?
Instead of a fixed averaging window, lowest performs local regression. For each single point in your time series, lowest looks at its neighbors.
How many neighbors?
That's controlled by a key parameter, the bandwidth. It's usually a proportion of the total data points.
Oh, okay.
Then it fits a regression line, often just a simple linear or maybe quadratic regression, but only to those neighboring points. And importantly, it's a weighted regression.
Weighted? How so?
Points closer to the target get more weight in fitting that local line, while points further away, but still within the bandwidth, get less weight. The fitted value from that local weighted regression becomes the smooth value for that single point.
So it builds the smooth curve point by point using only nearby data for each point.
Exactly. You repeat this for every point in the series. And that bandwidth parameter is the crucial tuning knob.
Controlling the smoothness.
Right. Looking at very few neighbors, the fit is highly localized, and the resulting curve can be very wiggly, potentially overfitting to noise. It means you're looking at many points, maybe almost all of them, and the curve becomes much smoother, potentially over-smoothing and missing local features.
That feels like a significant step up in flexibility. This seems to bridge us from visualization into methods really designed for modeling and, crucially, for forecasting. Let's talk about exponential smoothing, ES.
Yes, exponential smoothing is definitely more model-based, and it's particularly well-suited for forecasting, especially when you need to generate many forecasts very efficiently.
How does it work? Is it still averaging?
It is fundamentally an averaging technique, but with a key difference from the simple moving average. ES uses unequal weights.
Okay.
Specifically, the weights applied to past observations decline exponentially as you go further back in time. The most recent observation gets the highest weight, the next most recent gets a bit less, and so on.
So the idea is that the recent past is more relevant for the future than the distant past.
Precisely. That's the core assumption. It makes intuitive sense for many time series.
What's the simplest form? Say, for data that just has random noise around a constant level, no trend, no seasonality.
That's called single exponential smoothing, or simple exponential smoothing. You're essentially just estimating the current level or mean of the series. There's only one equation and one smoothing parameter, usually called alpha.
What does it control?
Alpha is the weight given to the most recent observation. So if alpha is close to 1, you put almost all the weight on the latest data point, making the smooth series react very quickly to changes. If alpha is close to 0, you put most of the weight on the past smooth values, resulting in a very smooth, slow-moving estimate.
But most series aren't just flat. What about trends?
Right. When there's a clear trend, a persistent upward or downward slope, single ES isn't enough. We need Holt's linear exponential smoothing.
Holt's linear, what does that add?
Holt's method estimates two components dynamically: the current level, like single ES, and also the current trend or slope. So now you have two updating equations.
And two parameter.
Exactly. You still have alpha for smoothing the level, and now you add a second smoothing parameter, usually called a beta, for smoothing the trend component. You update both the level and the trend estimate at each time step based on the new observation. The forecast then involves projecting forward using both the latest level and the latest trend estimate.
Makes sense. Track both level and slope. And the final piece of the puzzle, seasonality.
That brings us to the Holt-Winters procedure. This extends Holt's method to handle seasonality as well.
So a third component.
Yes. We now estimate and update three things: the level, the trend, and a seasonal component. And you guessed it, we add a third smoothing parameter, typically gamma, to control the smoothing of the seasonal factors.
Level, trend, seasonality, each with its own smoothing constant.
Correct. And just like with classical decomposition, you need to decide upfront if the seasonality is additive, constant size swings, or multiplicative swings proportional to the level. There are slightly different sets of updating equations for additive Holt-Winters versus multiplicative Holt-Winters. It's a very powerful and widely used forecasting framework.
Okay, that covers the ES family. Now, let's pivot entirely. What if we don't try to estimate the trend flexibly using smoothing, but instead assume the trend follows some kind of fixed, predictable mathematical shape?
Now you're talking about a different philosophy. This is where we assume the series is trend stationary. The idea is that underlying the noise and seasonality, there's a deterministic, non-random trend.
And how do we model that?
The most common approach is polynomial regression on time. You literally use time as your predictor variable in a regression model.
Linear trend.
Exactly. Or maybe quadratic trend, or higher order polynomials if needed. You specify the shape you think the trend follows, and then you estimate the coefficients using standard ordinary least squares, OLS regression.
The advantage being simplicity and easy interpretation.
Simplicity, interpretability, and very easy extrapolation for forecasts. The big assumption, of course, is that the trend really follows that specific polynomial shape.
And how do you incorporate seasonality into this regression framework?
The standard way is seasonal regression using dummy variables.
Dummy variables, you mean indicator variables.
Precisely. For each season, if you have monthly data, or each quarter for quarterly data, you create a variable that's 1 if the observation falls in that season and 0 otherwise.
So for monthly data, you'd have 12 dummy variables.
You'd create 12, but here's an absolutely critical point. You must drop one of them before putting them into the regression model.
Always drop one. Why is that?
It's because of perfect multicollinearity, also known as the dummy variable trap. If you include a dummy for every single season, plus an intercept term, the sum of all the seasonal dummies for any observation will always be 1. This creates a perfect linear dependency with the intercept column, which is also all ones.
The math breaks down. The model can't distinguish the effect of the intercept from the combined effect of all seasons.
Exactly. The model becomes unidentifiable. You can't estimate unique coefficients, so you always omit one seasonal dummy. Its effect is implicitly captured by the intercept term relative to the included dummies.
Got it. That's the standard way. Is there an alternative to these indicators for seasonality and regression?
Yes, especially if the seasonality is smooth and very regular, you can use Fourier series.
Sines and cosines.
That's right. Instead of dummy variables, you add pairs of sine and cosine terms as predictors in your regression model. These trigonometric functions are naturally periodic. You choose the frequencies, like cycles per year, to match the seasonality you expect. 1 cycle per year for annual seasonality, maybe more for intra-year patterns.
So it models the cyclical ups and downs using smooth waves instead of step changes from dummies.
Correct. It can be a more parsimonious way to capture smooth seasonality, sometimes requiring fewer parameters than dummy variables, especially for high-frequency seasonality like daily data with weekly patterns.
Okay, that parametric approach is clear. Now let's swing back towards non-parametric flexibility, but maybe even more sophisticated than Lois. What about generalized additive models, or GAMs?
GAMs, yes. They represent a very powerful and flexible approach, sort of blending ideas from regression and non-parametric smoothing. They are particularly useful when you suspect nonlinear relationships, but don't want to pre-specify a polynomial form.
How do they achieve that flexibility?
Instead of assuming a global functional form like a polynomial, or just local lines like a Lois, GAMs model the relationship using sums of smooth, non-parametric functions of the predictor variables. Often, these smooth functions are built using things called B-splines.
B-splines, what are those conceptually?
Think of B-splines as building blocks. You define a sequence of points along the time axis called knots. B-splines are simple, localized polynomial functions defined over the intervals between these knots. They're designed to join together smoothly at the knots.
So like fitting simple curves piece by piece between the knots and making sure they connect smoothly.
That's a great way to think about it. You basically represent the smooth function for the trend as a weighted sum of many of these simple B-spline basis functions. The model estimates the weights for each B-spline piece.
But if you're estimating all those beta coefficients, doesn't that make it parametric?
That's a subtle point. While you are estimating potentially many parameters, the resulting function itself isn't constrained to a simple named mathematical form like linear or quadratic. Its shape is determined data-drivenly by how these basis functions combine, considered non-parametric or semi-parametric. The additive part of GAM means you model the expected value as a sum, maybe an intercept, plus a smooth function of time for the trend, plus perhaps another smooth function for seasonality.
So incredibly flexible, allows nonlinear shapes, but maintains that additive structure.
Precisely. It gives you immense flexibility to capture complex patterns without forcing them into rigid shapes.
Okay, all these methods we've discussed, moving averages, LOES, ES, polynomials, GAMs, they're all focused on estimating or modeling the trend and seasonality. Now let's contrast that sharply. What's the simplest, maybe most brute force way to just get rid of a trend?
That would be
Differencing.
exactly. Differencing is the go-to tool when you believe your time series is different stationary, not trend stationary.
What's the key difference there again?
A trend stationary series has a deterministic trend that we can model, like with regression. A different stationary series has a stochastic trend. Think of it like a random walk with drift. The trend itself isn't predictable. It wanders randomly. You can't model it with a fixed function, so instead of modeling it, you eliminate it.
How do you eliminate it? We need some notation here, right? The backshift and difference operators.
Yes, they make life easier. The backshift operator simply means go back one time step.
Okay, shift back one.
The difference operator means take the difference between the current value and the previous value.
So first order differencing is just calculating the change from one point to the next.
Correct. And if your series has a linear stochastic trend, like a random walk with drift, taking the first difference will often remove that trend, leaving you with a stationary series. If the trend is more complex, like quadratic, take the difference of the differences.
But wait, if you difference, aren't you throwing away information about the trend itself? Why would you choose to just eliminate it instead of modeling it with, say, regression or a GAM?
That is the absolute core trade-off. You choose differencing when your primary goal isn't to model or forecast the trend component itself, but rather to make the remaining series stationary so you can model that stationary part, often with something like an RMA model.
So differencing is often a pre-processing step for other models that require stationarity.
Exactly. It's often the simplest and most effective way to achieve stationarity for a different stationary series without making strong assumptions about the trend's functional form. You're essentially saying, I don't care about modeling the wandering trend, I just want to analyze the stationary fluctuations around it.
And you can combine differencing for trend and seasonality.
Yes, the operator notation is neat for that. If you have, say, strong 12-month seasonality and maybe a quadratic trend, you might apply both seasonal differencing and second-order regular differencing together. The combined operation aims to remove both sources of non-stationarity simultaneously. Purely focuses on elimination.
It's a really clear distinction, modeling versus elimination. We've covered a huge range of approaches here.
We really have. From the fairly simple visual tools like moving averages and the more flexible LOES, then into the model-based forecasting powerhouse of exponential smoothing, across to the rigid assumptions of polynomial regression, the sophisticated flexibility of GAMs, and finally landing on the starkly different approach of differencing for elimination.
So wrapping this up, what's the bottom line for you, the listener, trying to navigate this? How do you choose?
I think the main takeaway is that your choice is driven entirely by two things: your analytical goal and the underlying nature of your data, especially the trend. If your main goal is efficient, large-scale forecasting, especially short-term, exponential smoothing methods are often the way to go. If you have a strong theoretical reason to believe the trend follows a specific mathematical shape and you need to interpret or extrapolate that shape, polynomial regression fits the bill.
And if you need flexibility,
if you need to capture complex, nonlinear patterns without making strong assumptions, GAMs offer incredible flexibility. And crucially, if you suspect your trend is stochastic, not deterministic, and your goal is simply to achieve stationarity for subsequent modeling, then differencing is probably the correct first step.
that frames the choice nicely. Okay, let's leave our listeners with a final thought to chew on.
All right. We've talked a lot about how to estimate or remove trends in seasonality. But perhaps the most fundamental decision you make happens before you even pick up a tool. You have to make a judgment. Is the non-stationarity in your series primarily due to a deterministic trend, making it trend stationary? Or is it driven by a stochastic trend, making it different stationary?
Because that initial assessment dictates everything that follows.
Absolutely. Getting that distinction right, trend stationary versus different stationary, tells you which entire family of techniques is appropriate. Misdiagnosing the type of trend at the start can lead you down a completely wrong analytical path. That distinction is arguably the bedrock of classical time series decomposition and modeling.